Okay, so we'll discuss the PLA programmable logic array in this section. And PLAs basically implement functions that are sum of products, much like this one. And there is a fundamental difference between PLAs and ROM that we studied early in this chapter. Basically, ROM implements minterms or implement minterms or max terms. But the PLA, the programmable logic array, we kind of implement sum of products. Okay, sum of products, and those are they could be minterms like this function, or they could be simplified terms. In the ROM, you cannot have simplified products. We have to have all minterms or max terms. But here I can have simplified expressions, and PLA leads itself into simplified hardware. To implement the PLA, basically we have two planes. One plane is called the AND plane, and the AND plane generate the products, these terms, right? And you can see here, this is BC, AC, AB, and the rest of those. And those happens to be midterms, but they can be otherwise. And then we have the OR plane where we do the ORing. Okay, so in this case, I need to OR these three terms, okay, to generate C out, and I need to OR these terms to generate the sum. And between these two planes, you can see that the layout is so organized, the logic is so organized that here are the products and here are the sums of the products. Okay, so to generate these two functions. So happens that here we are having a full adder function, but you can have any function you want. Okay, now for that, we can have NOR PLAs, and what they mean by NOR PLA is that if you have a kind of AND gate and followed by an OR gate, in VLSI we prefer to have NOR gates because they are faster. So you can implement this as a NOR gate, okay, with inverted inputs, okay, and this is easily verified by De Morgan law, by the way, and you can implement this by a NOR gate followed by an inverter. Okay, so this is basic. So I'm after these NOR gates. Those NOR gates are fast, but notice that here we have to invert the inputs. Okay, all right. So if we go back to what we have discussed earlier, so you can see that here this is this is an OR gate right here. Okay, all right, but with inverted inputs. So now to generate BC, all right, notice what I'm feeding. I'm feeding C prime and B prime. Okay, all right. So because once I have a B prime and C prime, okay, logically this will be B prime or C prime, okay, all under NOR, and this is equals to B ANDed with C. And this is exactly what I want using De Morgan's law. Similarly, this is how I generate A, C. So I use inverted inputs for these NOR gates. Now, in terms of how we implement it in hardware of transistors, look how we implement this NOR gate. You can see here, this is the BC function, right? Okay, all right, and this is your so the BC function basically is implemented if this is the pseudo NMOS, right, logic, and then you have here the wide NOR gate. So you have here the the B prime and C prime. The output here is BC. That's exactly what you have in terms of all the circuit right here. Okay. Similarly, you can implement the AC output and the AB and ABC, A prime, B prime, C, AB prime, A prime, B, C prime, A, B prime, C prime. And then you implement this NOR gate similarly for these guys. Okay, so again, this is the NOR gate which implements the sum prime, and we invert it for to get sum. This is the NOR gate implement the C out prime. We invert it to get the C out. Okay, so this is basically OR NOR gate. Again, why do we like NOR gate? They are faster. They tend to be smaller. Look at the ground here, all shared ground. So they provide much compact design, and we prefer them over NAND gate, which they are a bit slower. Okay, so and I say the NOR are smaller because all these transistors are sized to minimum size, you know, so because they are connected in parallel, but unfortunately the ground line adds to the area, so you know, a little trade-off probably with the area. Um, while we can maintain minimum size for transistors, we have to increase a bit the area for the tracks for the ground. Okay. Um, in terms of dot diagram, by the way, in my last lecture or the previous, I said stick diagram should be dot diagram. You can see here how I'm connecting for A, B. I connect the B prime with the C prime to get AB. For the AC, the A prime, C prime. So that provides for me this. And for the AB, I connect the A prime, B prime, okay, and I get AB. Now I connect the AB and AC, all these I connect them to generate the C out function, and similarly for the sum. Okay, so notice the AND plane and the OR plane. Okay, now the fundamental difference between, as we said, the OR the OR plane of the PLA is like a RAM, okay, which is basically which is basically this one here, okay, but it's the difference is actually in here. The AND plane of the PLA like RAM, but here is the key thing. PLAs are more flexible than ROMs. We don't need to generate all the 2 to the n rows of inputs, because the 2 to the n, they generate either the minterms and maximums. Remember, we need a decoder that generates all the minterms or maximums. That decoder becomes massive for large input. Okay, we only generate the minterms or the products that we need. And also we can simplify the logic in the case of the PLA. In the case of ROMs, we cannot simplify the logic. This is basically the difference. This is the major differences here. The simplification is allowed for in the case of the PLA, but in the case of the ROM, we use minterms or maximums without simplification. Okay, with that, thank you very much, and that concludes the section for PLA.